Good afternoon, dear friends. Today we will be compensating for the Monday session we haven't been able to do. So we are continuing in our Chiang book with 6.5 and 6.6 and 6.7. 6.5 is about inequalities and absolute values. Probably those are topics that you have already studied, you already know quite a lot. All right. So about inequalities and absolute values, it will be a kind of recalling session. The main rules of inequalities are the transitivity. When A is greater than B and B and greater than C, then A is greater than C. When A is greater or equal to B and B is greater or equal to C, then A is greater or equal to C. This is called the transitivity. There is also reflexivity and symmetry, but you probably know them already. Transitivity is perhaps the most important property of inequalities. And we can form continued inequalities thanks to transitivity. When, for instance, 3 is less than A less than B, then we can write down, and B is less than 8, for instance, then we can write down such a thing. 3 is less than A less than B and less than 8, you see. Or we can also write down 7 less than or equal to x less than or equal to 24, to mean that x is situated between 7 and 24. It can be any real number between 7 and 24, including 7 and 24. The frontiers, the end points are also included if we write down in this way as less than or equal or greater than or equal. We allow for equality as well. The rule 1 is about addition and subtraction of inequalities. When A is greater than B, and taking just a k, a real number k, and adding it to both sides of the inequality doesn't change. A plus k would be greater than B plus k. If A is greater than B, then A plus k would be greater than B plus k, whatever be the k, any real number. Similarly, A minus k would be greater than B minus k. When A is greater than B and greater than C, then A plus k would be greater than B plus k, greater than C plus k. And similarly, A minus k would be greater than B minus k, would be greater than C minus k. All these are possible. Rule 2 is about multiplication and division. Here the main rule is that when we multiply or divide an inequality by a negative number, the sense of the inequality, the direction of the inequality changes. Less than becomes greater than becomes less than. So we should be careful about this. When A is greater than B, and if K is positive, K is greater than 0, then K times A would be greater than K times B. But if K is negative, then K times A would be less than K times B. Just pay attention. As an example, we can see 6 greater than 5. So 3 times 6 is greater than 3 times 5, which is 18 greater than 15. This is the normal course of the things. But if we multiply 6 greater than 5 by minus 3 on both sides, then we obtain minus 3 times 6, which is minus 18, less than minus 3 times 5, which is minus 15, you see? And it is the same for division as well. So whenever we multiply or divide, division, in fact, is a multiplication by 1 over n. To divide a number by n, by another number n, means to multiply it with 1 over n. In fact, we have two operations, addition and multiplication. Subtraction is the addition with the inverse, with the opposite number, and division is multiplication by the inverse. So in reality, we have two operations, not 4. All right, algebraic operations, I mean. Rule 3 is taking the square. Here again we should be careful, because when a is greater than b and b is greater or equal to 0, then a square is greater than b square, alright. But the general rule is that if absolute value of a is greater than absolute value of b, then a square would be greater than b square. But if absolute value of a is less than absolute value of b, then a square will not be greater than b square. Just pay attention here as well. Be careful here. Because the important here is how close to 0 is the number. You see, well, for instance, when 2 is greater than 0, when we square both sides of it, then 4 is greater than 0, alright. But when 2 is greater than minus 3, when we take the square of them, 2 square is 4, minus 3 multiplied by minus 3 square is 9, and 9 is greater than 4. It changed sense, you see, it changed direction. So we should be careful about it. Alright, what about absolute values and inequalities? In fact, we can also express absolute values by some inequalities. They are very much related. So, first let's start by intervals. When we write down an interval like this, a, b, open interval, we call it open interval, and we denote it with these soft parentheses. When we write it like this, with soft parentheses a, b, it means it is defined as all the real numbers, x is a number of real number, such that a is less than x less than b. This is the definition of the open interval AB. All the x's, all the real numbers between a and b excluded. We don't include a and b. But if we write it down like this with square brackets, then a comma b in square brackets means all the numbers, all the real numbers, x belonging to the set of real numbers, such that a is less than or equal to x less than or equal to b. So we allow the x to be equal to the frontiers, to a and b as well. The endpoints are also included in the set, in the interval. For instance, when we say we have also semi-open and semi-closed intervals, if you recall. Semi-open or semi-closed means from one side it is square bracket, and from the other side it's a soft bracket, which means wherever there is soft bracket, this part is not included, this end is not included, but wherever there is square bracket, this part is included. If one side is included and the other side, one end is included and the other end is not included, it's a half open or half closed bracket, half closed interval. So the open interval minus a is defined as all the real number x's, so that minus a less than x less than a. And this can be also expressed as absolute value of x is less than a. Indeed, absolute value shows the distance of a number from 0. The distance, whether it is always positive, even if the number is negative, the absolute value returns the positive value. So it shows a distance, the distance of the number from 0. So x is less than a greater than minus a is, note that they are symmetric frontiers, minus a and a, they are symmetric with respect to 0. So x is greater than minus a and less than a means absolute value of x less than a. For instance, minus 10, 10, the open interval minus 10, 10 can be expressed as absolute value of x less than 10, you see. The absolute value, or the modulus, it's also called modulus in Latin, it shows the distance from 0. It is a function. The absolute value of n is such a function that it assigns the value n if n is positive. It assigns the value minus n if n is negative, and it assigns the value 0 if n is 0. This is the function absolute value. Well, for instance, minus 15, absolute value of minus 15. Since we have minus 15, a negative number inside the absolute value, we should, in order to calculate its absolute value, then we should multiply it with minus 1. So it becomes minus 15, which is plus 15. The absolute value, we can put positive or negative numbers or even 0 in the absolute value, but the value it gives, the value of the function will be always positive. So absolute value of minus n and absolute value of n are equal, of course. When we write down absolute value of x less than n, it is equivalent to minus n less than x less than n when n is positive. Again, if we write down absolute value of x less than or equal to n, we mean minus n less than or equal to x less than or equal to n for n greater than or equal to positive. You see, this is the meaning of the absolute value. And we have also some properties, the triangle inequality, which means absolute value of m plus absolute value of n is always greater than or equal to absolute value of m plus n. So if we sum up and then take the absolute value, it will always be less than or equal to the absolute value of m plus absolute value of n. So this is, or absolute value of m plus absolute value of n would always be greater than or equal to absolute value of m plus n. This is triangle inequality. Besides, absolute value of m times absolute value of n would amount to absolute value of m times n. Similarly, absolute value of m over absolute value of n, which means divided by absolute value of n, would be equal to absolute value of m over n. You see, and these are formulae which we can use for simplifying some operations. Some examples here: m is 5 and n is minus 3. Then absolute value of 5 plus absolute value of minus 3. Absolute value of minus 3 is 3. Absolute value of 5 is 5. 5 plus 3 is 8. And what is absolute value of 5 minus 3? 5 minus 3 is 2. Its absolute value of 2. 8 is greater than 2. You see an example for the triangle inequality. Besides, for the multiplication and division cases, we can give some examples as well. When m is 7 and n is 8, the absolute value of m times absolute value of n is 7 times 8, which is 56. And when we multiply them beforehand, 7 times 8 is 56. When we take its absolute value, it is 56 again. So it doesn't matter if we first take the absolute value and multiply, or first we multiply and take absolute value. You see, here you have these calculations, the same thing. Absolute value of m times absolute value of n is minus 7, absolute value of minus 7 times absolute value of 8, which is 7 times 8, 56. But if we multiply beforehand, minus 7 times 8 is minus 56. Its absolute value would be 56 again. All right. So, let's see. So how we solve inequalities? As we solve inequalities, we can also solve inequalities, the solution of an inequality. What does it mean to solve an equality or inequality? It means to find the values, the set of values satisfying this equality or inequality. So we should find all the values, the set of all the values which satisfy this inequality. The solution is also expressed as an inequality indeed, or an interval. Inequalities can also be expressed by intervals most of the time. So the example: solve the given inequality. 3x minus 3 greater than x plus 1. What shall we do? Well, as we solve equalities, we will just try to leave x alone and all the other exogenous numbers, exogenous sort of coefficients to the other side. So what can we do? We can first add 3 to this both parts of this inequality. 3x minus 3 plus 3, and then also subtract minus x from both parts. Why? To leave the x's on the left hand side and the numbers on the right hand side. So we can add plus 3 to both sides of the equation of the inequality, and add minus x to both parts of the inequality. Then the inequality would not change. We just add numbers. We just add expressions. So the direction of the inequality would not change. 3x minus 3 plus 3 minus x would be x plus 1 plus 3 minus x. So on the right hand side, x minus x would be 0. It will disappear. 3 plus 1 is 4. And on the left hand side, minus 3 and 3 annihilate each other. It becomes 0. That disappears. 3x minus x is 2x. So 2x greater than 4. And we multiply both sides by 1/2, which means we divide both sides by 2 to obtain x greater than 4 over 2, which is 2. X is greater than 2 is the solution set. We can also express it as the open interval 2 plus infinity, and note that the infinity part is always open. We can never reach infinity, so the infinity is always open. 2 could have been closed, but in this case, since there is strict inequality, 2 is open as well. So x is greater than 2 is the same as the open interval 2 plus infinity, or the set x is an element of R such that x greater than 2. This is also another expression. Well, another example, solve the given inequality, absolute value of 1 minus x less than or equal to 3. All right. So if absolute value of 1 minus x is less than or equal to 3, we can write it down as we have seen above. Minus 3 less than or equal to 1 minus x less than or equal to 3. You see? Whatever in absolute value, I mean, we can open it and we can say when 1 minus x, absolute value of 1 minus x is less than or equal to 3, then 1 minus x itself cannot be further to 0 than 3. So it is either in the interval minus 3, 0 or in the interval 0, 3. So it means minus 3 less than or equal to 1 minus x less than or equal to 3. This is the way how we open this inequality, this absolute value. All right. Then what shall we do? We should add minus 1 to both sides of this inequality. Minus 3 minus 1 is minus 4. 3 minus 1 is 2. And 1 minus x minus 1. 1 and minus 1, they cancel each other. We are left with minus x. So minus 4 less than or equal to minus x less than or equal to 2. But in order to obtain x, we should multiply both sides by minus 1. Which means we should also change the direction of the inequalities. When we multiply by minus 1 times minus 4 is 4, minus 1 times 2 is minus 2, and minus 1 times minus x is x. But the sense of the inequality, the direction of the inequality will change since we multiply by a minus 1, which is a negative number, 4 greater than or equal to x greater than or equal to minus 2. So this is the solution set. Or we can also write it down as minus 2 less than or equal to x less than or equal to 4. Or as the set x real number is in fact we should have said x is an element of real numbers such that minus 2 less than or equal to x less than or equal to 4. Or simply the closed interval minus 2, 4. All these mean the same thing. Alright. Here there are some exercises. You should just make them, and I sent you as well. I mean, in our course page, we have also the solution book of these exercises, so you can try yourself and then look at the solutions. And whenever you don't understand or you don't doubt about something, then you can call me up, or you can send me an email or a WhatsApp or Telegram message to ask me about what you doubt. All right. So we are at 6.6 now, the limit theorems. Well, here we have the delta and epsilon things. Delta and epsilon. We have spoken about delta and epsilon neighborhoods. We will be using them here as well. So theorems involving a single function. Q equals g of v, or we can also express the same thing as y equals f of x. But our book, for some reason, prefers q equals g of v. In the usual mathematics books, we always use y equals f of x, of course. This is the same thing. All right. The theorem 1 says when a and b are real numbers, q and q is equal to a times v plus b, which is a linear function of v. We could have said also y equals a times x plus b. It would be the same. Limit of q when v goes to n is a times n plus b. A times small, big case letter n plus b. So limit, I repeat, when q is av plus b, limit of q when v goes to n is a times n plus b. Let's prove it. This is a simple but interesting proof and interesting formula, because it is the basis of all polynomials, so we should be able to understand and prove it. The proof goes like this. We have to consider two cases: when a, the coefficient of n, is greater, or v is greater than 0, and the case where a is less than 0, because it changes the sense of the inequality. So when a is greater than 0, let's choose delta equals epsilon over a. Delta and epsilon should be positive. Don't forget, we have seen this before, and we have used them in some proofs. Delta and epsilon are very small distances, infinitesimal, infinitely small distances, but positive. So delta, let's choose delta equals epsilon over a. A is positive, epsilon over a, epsilon is positive, epsilon over a, which is delta, is positive as well. And q is between L minus epsilon, L plus epsilon. If it is so, let's show that whenever v is between n minus delta, n plus delta, in the interval n minus delta, n plus delta, then q would be between L minus epsilon, L plus epsilon. This is the logic of our proof. So what shall we do? L is our conjecture, or our claim is that q, limit q, this L is the limit of q, it should be equal to a times n plus b. So if it is so, L minus epsilon would be a times n plus b minus epsilon, and L plus epsilon, L minus epsilon is a times n plus b minus epsilon, L plus epsilon would be a times n plus b plus epsilon, and q is av plus b. So av plus b should be between, a times n plus b minus epsilon should be less than a times v plus b, less than a times n plus b plus epsilon. So if we subtract minus b, if we add minus b to both parts of this inequality, we would obtain an plus b minus epsilon less than av plus b minus b less than an plus b minus b plus epsilon. So these b minus b's, they cancel each other. What are we left with? It is an minus epsilon less than av, a times v, less than a times n plus epsilon. And since a is positive, if we divide both parts by a, we obtain a by a is 1, so we remain with n here, minus epsilon over a, less than a times v over a's cancel each other, a over a is 1, so we are left with v, and a times n plus epsilon, when we divide it by a, we obtain n plus epsilon over a. So our v is between n minus epsilon over a and n plus epsilon over a, meaning n minus epsilon over a less than v less than n plus epsilon over a. So, and what have we chosen? How have we chosen d? D is equal to epsilon over a, and so here we obtain d, and here again. So n minus delta, delta, the Greek d. It is the small case d letter in the Greek alphabet, delta. So we obtain n minus delta less than v less than n plus delta. But here we have proven what our claim. When q is between L minus epsilon, L plus epsilon, v can be squeezed between n minus delta and plus delta. And so that its function value, av plus b, is between L minus epsilon, L plus epsilon. So we have proven. So limit q when v goes to n is really an plus b. When a is negative, then we should be careful here. Let's choose delta equals to minus epsilon over a. Why? Because a is negative, epsilon is positive. Epsilon over a would be negative, but delta should be positive, so we should multiply it with minus. So we should choose delta as not epsilon over a, but minus epsilon over a. Be careful. All right. Then the logic of the proof is the same, but we should just take care that we have a minus sign here. So an minus epsilon, which is the proof goes on as in the previous case. We say L minus epsilon less than q less than L plus epsilon. So an plus b minus epsilon is less than av plus b plus less than an plus b plus epsilon. And then subtract b from both parts. An plus b minus b minus epsilon less than av plus b minus b less than an plus b minus b plus epsilon, and we are left with an minus epsilon less than av less than an plus epsilon. Here we should be careful because now we will divide by a to obtain, to leave v alone. But in this case, so we are here up to here, you see an minus epsilon less than a times v is less than a times n plus epsilon. But then we divide both parts, all parts, by a. So, and a is negative, don't forget. So when we divide the inequality by a, then the direction of the inequality should change. So a by a will be 1, and here we are left with n minus epsilon over a. When we divide a by v by a, then a over a is 1, it disappears, we are left with v. And a times n plus epsilon, when we divide the whole by a, we obtain n plus epsilon over a. But careful, we have to change the direction of the inequalities. So n minus epsilon over a should be greater than v, should be greater than n plus epsilon over a. You see? But what is our delta? Our delta is minus epsilon over a. We have chosen delta this time as minus epsilon over a. You see? So n minus epsilon over a is n plus delta. It is not n minus delta, but n plus delta. And n plus epsilon over a is now n minus delta, because our delta is minus epsilon over a. So we obtain, again, n plus delta greater than v greater than n minus delta, or n minus delta less than v less than n plus delta. This is the end of proof, which means when an plus b, when q is between our limit candidate an plus b minus epsilon plus epsilon, then we can squeeze v between n minus delta, n plus delta, choosing delta as minus epsilon over a. And so that the image of v is a times v plus b, whose limit is an plus b. So we have proven that limit q when v goes to n is a times n plus b. Well, these proofs are a little bit tricky. I understand they are not very easy to perhaps understand. There are even more complicated proofs than these, but this much is enough for the purpose of this course. We will be concentrating on the applications rather than proofs. Anyway, it's good to see the proof of the theorem as well. So the example, our example 1 is q is equal to 5v plus 7. 5 times v plus 7. What is its limit when v goes to 2? Very simple. We just replace v by 2. 5 times 2 plus 7, which is 10 plus 7, 70. You see, very easy. So the theorem 2 is about the constant functions. In fact, it is a corollary of the previous theorem. If q is equal to g times v equals to b, so the function is a constant function b, then limit q when v goes to n is b. Well, or you can also express the same thing as y is equals to fx equals to b. This is the constant function whose value is b. And its limit for v going to any n would be b, its value, and would not change. Its limit would be its value anyway. But here in the previous case, in the previous theorem which we had proven, if we take a is 1, no, a is 0, I mean, if we take a is 0, then a times v would be 0, and we will be left with q equals b, or g of v equals b, or y of x equals b. So this is a special case of this general theorem. So we don't have to prove it again. We don't have to prove it again. Theorem 1 implies theorem 2. If we have theorem 1 in hand, which we have proven, then we can just choose a as 0, and we obtain the theorem 2, of course. Very easy. Alright, theorem 3. If q is v, then limit q when v goes to n is n. You can also say when y is equals to f of x equals x, y equals x, the 45-degree line, then limit f of x when x goes to n would be n. And similarly, if q is equal to v to the power k, then limit q when v goes to n would be n to the power k. Well, an example, we will not be proving them. These proofs are a little bit more tricky than, well, the first one is not. Also, if q is equal to v, then limit q when v goes to n is a special case of the theorem 1 which we have proven. There we can take b as equal to 0 and a equal to 1, then we would obtain q equals v. So it is also a special case of the theorem 1. But for q equals v to the power k, so limit q is when v goes to n is n to the power k, we have to use the powers of epsilon and so on. It's not very well, it's not so difficult, but it's not very simple either as proof. Our book hasn't given the proof of it, so I skipped the proof as well. I just give you whatever the book gives you. Alright, the example 2 is given q equals v to the power 3. The limit of q when v goes to 2 is 2 to the power 3, which is 8. The application is very simple. Alright, and an important remark here. V goes to n is not equivalent to V equals n. V goes to n doesn't mean that V is equal to n. It means, in fact, it is never equal to n. It comes very close to n without being equal. V goes to n means V gets closer and closer to n, but never it becomes never equal to n. This is very important. So theorems involving two functions this time. If we have more than one function, two functions with every one with its own limit. So if limit q1 when v goes to n is L1, and if limit q2 when v goes to n is L2, then we have theorem 4, sum and difference limit theorem. What is it? Limit of q1 plus q2 when v goes to n is L1 plus L2. The limit of the sum of two functions is the sum of their limits. Similarly, the limit of the difference of two functions is the difference of their limits. Limit when v goes to n is of q1 minus q2 is L1 minus L2. You see? Besides, if we multiply the function with a constant real number, limit such as limit 2 times q1 when v goes to n, it will be the same as limit q1 plus q1 when v goes to n. Q1 plus q1 is 2q1. So using this theorem 4, L1 plus L1 would be 2L1. You see, when we multiply the function by a constant, we multiply its limit with the same constant as well. Limit of 2q1 when v goes to n is 2L1, if the limit of q1 is L1, of course. All right. And using these, we can also have the theorem 5, the product limit theorem. The limit of the product is the product of the limits. If both q1 and q2 have limits, L1 and L2, respectively, then limit of q1 times q2 when v goes to n, the product of the two functions when v goes to n, is equal to L1 plus L2, the product of their limits. The limit of the product is the product of the limits. For more than two functions, you can apply it as well. For 3, 4, any number of functions. So, a special case is when we multiply q1 by q1. Limit q1 by q1 when v goes to n would be L1 by L1, L1 multiplied by L1, which would give L1 square. So if we square a function, we square its limit as well. You see, if we take the third power of a function, the cube of a function, then we take the cube of its limit as well. You see, very easy. All right. So theorem 6 is quotient limit theorem. Limit q1 over q2 when v goes to n would be L1 over L2. The limit of the quotient will be the quotient of the limits, but under the condition that L2 would be different from 0. Of course, the denominator should not be 0. So L2, whatever is on the denominator, should be different from 0. The example 3 is find limit when v goes to 0 of 1 plus v over 2 plus v. What is limit 1 plus v when v goes to 0? When v goes to 0, 1 plus v goes to 1. When v goes to 0, 2 plus v goes to 2. So limit 2 plus v when v goes to 0 is 2. Limit 1 plus v when v goes to 0 is 1. So limit 1 plus v over 2 plus v when v goes to 0 is 1 over 2. You see, very simple. All right, and therefore the limit of a polynomial function. Using all these properties, we can now define the limit of a polynomial function. What is it? A polynomial q of g of v, of course, is a0 plus a1 times v plus a2 times v squared plus a3 times v cubed, etc. Plus up to an v times v to the power n, small cap n. So small case n. This is the general polynomial. And if we say that limit of v when v goes to n is big case n, then the first term a0 is a constant term. The limit of the constant is itself the constant itself, as we have seen above. So limit of a0 when v goes to n is a0. Limit of a1 times v, which is the linear term, we have seen that it's equal to a1 times n. When v goes to n, limit of a1 times v is equal to a1 times n. And for square, we just square the limit. If the limit of v when v goes to n is n, then limit of v square when v goes to n is n square. And when we multiply it by a2, it would be a2 times n square, etc. So for each monomial, these parts of the polynomial are called monomials. The sum of the monomials is a polynomial. So each monomial's limit is the value of this polynomial at the point big case n. All right. So what we obtain at the end, limit of the polynomial when v goes to n is a0 plus a1 times n plus a2 times n square plus a3 times n to the power 3, etc. plus up to a n times big case n to the power n. So the limit of a polynomial at the point n is the value of this polynomial at the point n. Limit of q when v goes to n is the value of that polynomial at the point big case n. Here again we have some exercises. You will make them, you will solve them, look up your solutions in the solution book, and if you don't understand something, just ask me. All right. So we are at 6.7, the continuity and differentiability of a function, which is of course an important topic. Both are important, but this is quite an important topic as well. What does it mean, the continuity? Intuitively, it means to be able to draw the function without taking the pen up at that point or at that region. So if I can draw a function, the graph of a function, without taking up my pen, my hand from the paper, then this is continuous. But what does it mean? I mean, how is it formally in mathematics? How can we express this formally? And note, this note is important as well. Determinacy of a function, definiteness, determinacy of a function, limit, continuity, differentiability of functions are pointwise properties. So they are valid at each point. We should check at each point if we could. We should have, I mean, we should check if we could at each point. But if a property is valid, if one of these properties is valid at one point in a function, it's not guaranteed that it would be valid in the point next to this. So we should be able to check for each point of the function in the domain of definition of the function. But usually we check for a typical point without making some conditions, some constraints, without putting some constraints on it, and we generalize this proof or this property to all the function in the throughout the function in its domain of definition. So q is g of v, our primitive function, when v goes to n. V will go to n. And here we have drawing some graphs as well, which we will study. Two graphs at the upper side are continuous, and the other two graphs at the lower side, two graphs down, are discontinuous. And we will see how they are. So the conditions of continuity. What is continuity? In order to be continuous, a function should have three conditions, should fulfill three conditions, which can be summarized in one condition indeed. The last condition is summarizes all of them. The first condition is n, the point n, should be in the domain of definition of the function, which means the function should be defined, should have a value at the when x is equal to n. So gn should be in the range of the function. G of n should be in the range of the function. When I put the for the value x or v, whatever, for the independent variable, the value n in the function, I should obtain a definite value which is in the range of the function. You see, this is the first condition. The second condition is that there should be the limit of this function at when v goes to n. So, which means also this amounts to three conditions. The limit from the right, limit from the left should exist and should be equal to each other in order that the limit of g of v exists when v goes to n. And the third condition, which summarizes all of them, is that this limit of g of v when v goes to n should be equal to g of n, meaning that the limit of this function at that point should exist and should be equal to the value of the function at that point. You see? So, is it possible that this third condition may not be fulfilled? Of course, there are many ways this third condition would not be fulfilled. Even if we have, in fact, we have both a value for the function is defined there, and it has a limit. This limit may be different from the value of the function at that point. For instance, the function can be defined as a singular point over, I don't know, we have a continuous function all over its domain, but at one point, this function would have a limit, but its value would be different from that. Its value would be higher or lower than the general drawing of the function, general graph of the function. So in this case, we can very well have limit of gv when v goes to n different from g of n, or the value of the function at that point. So let's see at figure 2 what is continuous and what is not continuous. Here at figure 6.2, a and b are continuous. A and b are the uppermost functions, the two functions over there. You see, I can draw this function without taking up my pen, and this one as well. And note that the limit of this function is L when v goes to n from left or from right. The value of the function goes to L. And the value of the function when x is equal to n or v is equal to n is L again. You see? So I can draw this function without taking up my hand. And again, here again, we have the value of the limit of the function from the left and from the right is L. Whenever I approach the n, v goes to n from left or v goes to n from right, the value of the function goes to L from below. And then the value of the function at the point x equals n or v equals n is L again. So the limit is equal to the value of the function at that point. So this function is continuous as well. Here we see at the lowermost two functions, we see two discontinuities. The first one is a step function. This function is called a step function. We have seen it before, perhaps. If not, you will learn here. It's called a step function. From when v comes from minus infinity up to n, the function is equal to L1. It's a constant function, L1. And when v goes from n to plus infinity, in this part, the function is equal to L2. It's again a constant function, L2. But L1 is different than L2. And here there is a mistake in the book. Actually, you cannot put a black dot in sort of filled dot in both points. corresponding to n. Otherwise, it wouldn't be a function. And an origin, a starting point, cannot have two or more images in a function. So one of these points should be empty, or an empty point, or we should put a half moon type thing to show that this part is empty. If the lower part, if we empty the lower part, the upper part can have a dot, a sort of full dot. Or if we lower part is full, then we should empty the upper part. This both ends here cannot be full, both of them. Otherwise, this would not be a function. Anyway, so what are the limits of this function from the left and from the right? Where here, the limit of this function from the left is L1. When you approach n from minus infinity, when you come closer and closer to n, the value of the function is L1 and its limit is L1. But when you approach n from above, from the right hand side, then the value of the function is L2 and its limit is L2. So both it has left hand side and right hand side limit. It has left limit and right limit, but they are not equal. So you cannot draw this function without taking your pen from the paper. So up the paper. So this function is discontinuous. Another kind of discontinuity is these asymptotic functions. The asymptote is a limit. It's a line, or it's a curve where the function approaches without touching, without crossing it, and it approaches infinitely small to this function, very close, where it gets closer, but it never crosses this line. So here we have an asymptote, you see, and here again. So m and n, the lines m and n are asymptotes of this function. So here again, this function, when v goes to n from above, meaning the right limit of the function is plus infinity. Left limit of the function when v goes n is minus infinity. Even if it went to plus infinity as well, it would have no limit at all, because infinity is not a limit. The limit is infinity, means it has no limit. It just augments, and augments. And here it diminishes, it goes to minus infinity. So this function has no limit. Therefore it is not continuous at the point n. But when the n goes to plus infinity, the function goes to m, you see, from above. So m is the limit of this function when v goes to plus infinity. And when v goes to minus infinity, the the value of the function approaches m from below. So the limit of the function when v goes to minus infinity is m again. But this doesn't mean anything. At the point n, it is discontinuous. It's not continuous anyway. All right. So what about polynomial and rational functions? Polynomials are defined and have limits everywhere, and their limit at any point is equal to their value at that point. So they are continuous everywhere, as we have seen before in this in the previous heading. So, but what about rational functions? Polynomials are easy to understand. So, whenever you put the value of when you calculate the value of a polynomial, it would be equal to its limit. The left limit and the right limit would be equal, and they would be equal to the value of that polynomial at that point. So, no problem. But for rational functions, we should be careful. It's not always said that they are continuous. What does the continuity theorem says? Here we have also a general theorem, continuity theorem. The sum, difference, product, and quotient, of course the denominator not being zero, of a finite number of functions which are continuous in their respective domains are also continuous. Thus, a rational function is also continuous wherever it is defined. This is important. It should be, we cannot say anything for the region where it is not defined. The denominator should not be 0 anyway. Otherwise, it will not be defined. So, and well, unfortunately, here we have well, these frames have shifted a little bit. In the presentation, they are correct, but here, when we translate the presentation, when we load the presentation in this program, it shifts some of these frames, unfortunately. But we will, I will tell you what they are. So the example 1 is Q equals G of V equals 4 times V square over V square plus 1. This is a rational function. So what is its limit? First, is it defined? Yes, it is defined. Its domain of definition is R, because V square plus 1 can never be 0 in the real numbers. V square can be minus 1 only in imaginary numbers, not in real numbers. V square is always positive. Its least value can be 0. It cannot be less than 0. V square in a real space. So V square plus 1 would be always greater than or equal to 1. V square being positive. V square plus 1 would be always greater than or equal to 1, so it cannot be 0. There is no such a danger. So this rational function is defined everywhere in real, in the set of real numbers. So there is no problem with defining this. And what is its limit? Its limit is the limit of the numerator divided by the limit of the denominator, which is limit q when v goes to n is equal to limit when v goes to n of 4 to the power v square over limit when v goes to n to v square plus 1. Well, what is the limit of 4 square? So 4 times v square when v goes to n is 4 times n square. What is the limit of v square plus 1 when v goes to n is n square plus 1. So the limit of this function when v goes to n is 4 times n square over n square plus 1. But what is the value of this function at the point n? It is 4 times n square over n square plus 1, which is the limit of the function. So the limit is equal to the value of the function at that point, so the function is continuous, you see. But when we have q equals v to the power 3 plus v square minus 4v minus 4 over v square minus 4, then we are in trouble a little bit, because when v is 2 or minus 2, the denominator is 0. When v is 2, its square is 4, 4 minus 4 is 0. When v is minus 2 square is 4 again, 4 minus 4 is 0. So this function is not defined at minus 2 at v or x equals minus 2 and 2. So its domain of definition is all the real numbers minus the set minus 2, 2. So this function is defined in all real numbers but minus 2 and 2. So we should exclude minus 2 and 2 from its domain. This domain of the definition is real numbers minus 2 and 2. You see? So at these 2 points, although it's a rational function, it has limits, it has everything. We have also studied this function when we were studying limits. And we know that it can be simplified and this limit can be found. But the problem is that at the very point v equals minus 2 and v equals 2, it is not defined, it's not determinate, it's an indeterminacy. We don't know what it is, the function doesn't exist at these points. So we cannot draw it without taking our hand from the paper. This function is discontinuous, it's minus 2 and 2. Otherwise, it is continuous in all the other points, all the other real points. All right, and it has limits at this point also. Yes, for minus 2 and 2, there is a hole in the function, of course. A whole, of course, it should be without w, not a whole, but a whole, like there's nothing at that point in the function. All right. So, what is the differentiability of a function? Let's come to the differentiability of a function. Differentiable means whose derivative can be taken. When the derivative of a function exists at some point, it is differentiable there. Differentiability means derivability to its derivative exists. It means this. So the condition of continuity, a condition of continuity that the function is continuous, is a necessary but not sufficient condition of differentiability. What does it mean? Which means if a function is continuous, it's not necessarily differentiable, but it should be continuous first and differentiable afterwards. But if the function is differentiable, it may not be discontinuous. Any differentiable function is continuous, but any continuous function is not differentiable at any points. So we should be careful about it. And now we will prove it. We will show that it's a one direction implication, which means if the function is differentiable, if its derivative exists at point, it is continuous at that point. The implication, you see the arrow of the implication is in one sense. It's not double-sided, sort of double direction implication. It is one directional, unidirectional, unisense implication from the differentiability towards continuity. Any continuous function is not differentiable, but any differentiable function is continuous. So let's prove it. What does it mean? Continuity. In summary, in sum, it means limit of fx when x goes to x0 is equal to f of x0. Limit of the function at when x goes to that point x0, the specific point x0, is the value of that function at that point, f of x0. So this is the general formula of the general sort of rule of continuity, condition of continuity. This is the third condition we have mentioned above, and it sums up all the other conditions, which means there is limit, there is the function is definite at that very point x0, and the limit is equal to the f of x0, of the value of the function at that point. So this condition summarizes all the conditions. What is differentiability? That the derivative of this function exists at that point. And what is derivative? Derivative of f at that point, f prime x0, is equal to limit when delta x goes to 0 of delta y over delta x, which is the limit of the rate of variation or difference quotient of the function when delta x, when the change in x goes to 0. This is the definition of the limit, of the derivative, I mean. This is the definition of the derivative of a function at a point. F prime x0 is equal to limit delta x when delta x goes to 0 of delta y over delta x. And we can express it more explicitly as it is equivalent to limit when delta x goes to 0 of f of x0 plus delta x minus f of x0 over delta x. This is the condition of differentiability. If this quantity exists, the function is differentiable at that point. And just recall drawing our graph of the differentiability of the derivative. We have here n, which is x0, and x0 plus delta x gives us another x, another from n, different from n. The difference from between x0 plus delta x and x is delta x, or you can say the difference between x and n is delta x. And the function value of n is fn, the function value of x is fx, or the function value of x0 is f of x0, the function value of x0 plus delta x, f of x0 delta x. Those are the same things. F of x or f of x0 plus delta x is the same, and f of n or f of x0 is the same thing. in our book, it uses n. In most mathematics books, it would use f of x0 instead of f of n. Anyway, they say the same thing. And the difference of f of x and f of n is delta y. So delta y over delta x is this quotient delta y over delta x, which is the slope of the beam of the of this line between this point and the other point. So this is the slope delta y over delta x. When we take the limit of it, then we obtain the slope of the tangent line to the starting point, this point. You see? So let's recall it. All right. So let's prove that if a function is differentiable at a point x0 or n, then it is continuous, but not the inverse. All right. How can we prove it? Well, let's take x0 equals to n and x0 plus delta x as x, nex, x0 plus delta x. All right. When delta x goes to 0 and x goes to n. When delta x goes to 0, x goes to x0 or x goes to n. All right. So we can express the same rule for continuity as limit f of x when x goes to n as equal to f of n. This is the definition of continuity. When we take x0 instead of x0 we take n, and instead of x0 plus delta x we take x. So limit of f of x when x goes to n, if this is equal to f of n, the value of the function at that point, the function is continuous. And what is differentiability? The same thing expressed with n is f prime of n, the value of the derivative of n at that point, is equal to limit when x goes to n of f of x minus f of n over x minus n. So this is the differentiability of a function at any point n. And we note something. We note that fx minus fn is equal to, in fact it is equivalent to, more than equal but identically equivalent to fx minus fn over x minus n times x minus n. If x minus n is not 0, we can simplify these x minus n's. We are left with fx minus f of n. F of x minus f of n. So f of x minus f of n is really equal to f of x minus f of n over x minus n times x minus n. This is an observation, which is always true. Great. So what shall we do? Let's take the limit of this equation, both parts of this equation, and see what happens. You see, the left side will be here. It just jumped a little bit the book, but limit of f of x minus f of n. And what is the limit of f of x minus f of n? Limit of a difference of two functions. It is the difference of their limits. Limit of f of x minus limit of f of n. And what is the limit of the product of the of two functions? It is the product of their limits. So here at the right hand side we have a product, and its limit will be equal to limit of f of x minus f of n over x minus n when x goes to n times limit of x minus n when x goes to n. Let's see. You see, left side will be limit of f of x when x goes to n minus limit of f of n when x goes to n. This is the difference limit theorem. And limit of f of n is a constant. When we put n, when the value of the function at the point n is f of n, this is a definite and constant value. So when x goes to n, this limit will be equal to f of n. And limit of f of x when x goes to n, when it is the same as limit of f of x and x goes to n. All right. And the right hand side will be limit when x goes to n of f of x minus f of n over x minus n times limit when x goes to n of x minus n, the product limit theorem. You see, and we give all the sort of the reasons why, or the theorems or the rules according to which we can distribute these limits in this multiplication or sum or difference, whatever. So we should state how, in which, under which logic or under which rule we make this operation. So let's see. What do we obtain? We obtain limit of the left hand side is limit when x goes to n of f of x minus f of n. Great. The right hand side is limit when x goes to n of f of x minus f of n over x minus n. What is this? This is the derivative of this function f of x at that point, which is f prime n. You see, all these limit is f prime n. And here we have limit of the difference, which is the difference of the limits, which is limit of x when x goes to n minus limit of n when x goes to n. And what is limit of x when x goes to n is n. Limit of n when x goes to n is n again. So we obtain, all in all, f prime times f prime of n times n minus n. N minus n is 0, so this is equal to 0. So right hand side is equal to 0. What is left hand side? Limit of f of x when x goes to n minus f of n. So all these things is equal to 0. And what does it mean when we put the f of n to the other side, to the right hand side? We obtain limit of f of x when x goes to n is equal to f of n. Quod erat demonstrandum. This is what we were proving. This is a Latin word, Latin expression, meaning this was what we were trying to prove. Quod erat demonstrandum. All right. So we have all demonstrated, we have proven that when a function is differentiable, when it has a derivative at that point, it is continuous. You see, from differentiability, we reach to continuity. But from continuity, we cannot reach to differentiability, as we will see shortly in the in our last counter example. Counter example is an example showing that the continuity does not imply differentiability. A function can be continuous at a point, but may not be differentiable at that point. So our example is this one. It's an absolute value function. Y equals f of x equals absolute value of x minus 2 plus 1. If we draw this function, we obtain something like this. You can make it draw to your, you can draw by yourself, or you can make it draw to there are function drawer applications for cell phones or for computers, so you can make it draw, you can to any application like this. So it is the function y equals absolute value of x minus 2 the whole plus 1 is it consists of two linear parts, two lines, just uniting each other at the value of x, which is 2, 1. You see, at the point 2, 1, they intersect. It is their common value. Otherwise, from minus infinity to 2, it's a decreasing function. From 2 to plus infinity, it's an increasing function. Its slope is plus 1. From 2 to infinity, its slope is plus 1, its derivative is plus 1. From minus infinity to 2, its slope is minus 1, its derivative is minus 1. So let's see that it is so. Then, if its slope from one side this is minus 1, from the other side it is plus 1, the slope is the limit of the rate of variation, delta y over delta x. So you see, from one side, the limit of delta y over delta x is plus 1, and from the other side, it is minus 1. They are not equal, so the limit of delta y over delta x does not exist at that very point, 2, 1. So at that point, the function is continuous. I can draw it without taking my hand from the paper, but my pen, from the paper, but at that point, the function is not differentiable. It doesn't have a derivative at that point, because it has an infinity of tangent lines from ranging from minus 1 to plus 1, whose slope ranges from minus 1 to plus 1. You see. So let's prove it also algebraically. All right. What is the, well, is this function continuous? It's very visible that it is continuous, isn't it? It has a limit. The function x minus 2 plus the absolute value of x minus 2 plus 1 has a limit at the point t 2 1. At the point 2 1, it is defined 2 minus 2 is 0, absolute value is 0, 0 plus 1 is 1. So its value is 1 at the point when x is equal to 2. Then it's the value of the function is 1. There is no doubt about it. Great. And what is the limit of that function when x goes to 2 from above, for instance? 2 from above, 2 minus 2 is 0, plus 1 is 1. So, you see, sorry. All right. So, when x goes to 2 from above, then 2 minus 2 is 0. This absolute value goes to 0 from above, and 0, 0 plus 1 is 1. The limit of this function, the right limit of this function is 1. What is the left limit? When x goes to 2 minus from its minus side, from minus infinity, then here the value is 2 minus 2 is 0. It becomes 0 minus, but again its absolute value 0 plus. It doesn't change anything. It goes to 0, plus 1 goes to 1. So both from left and from right hand side, this function goes to 1, and the value of that function at this point, at the very point 2, when x is equal to 2, is 1. So its limit exists and is equal to the value of that function at that point. So it is continuous, no problem. What is the problem? The problem is that at that very point, its derivative doesn't exist. And let's show it algebraically. So what is the derivative of this function at that point? It is when its limit, when x goes to 2, of f of x minus f of 2 over x minus 2. So this is the definition of the derivative of the function. Here's this quotient is the quotient of difference of rate of change or rate of variation, and its limit when x goes to 2 is the derivative of this function at that very point. So f of x is absolute value of x minus 2 plus 1. F of 2 is 1. F of x minus f of 2 is absolute value of x minus 2 plus 1 minus 1. Plus 1 and minus 1 cancel each other. At the numerator, we are left with x minus 2 in absolute value. And at the denominator, we have x minus 2. X minus x0. x0 is 2, so x minus 2. You see? So we write limit. Always we write limit equals limit up to the end. So here we obtain limit when x goes to 2 of f of x minus f of 2 over x minus 2 is equal to limit x when x goes to 2 of x minus 2 absolute value of x minus 2 plus 1 minus 1 over x minus 2, which is equal to limit when x goes to 2 of absolute value of x minus 2 over x minus 2. Great. But when x goes to 2 from above to 2 plus, from its higher values higher than 2, then the absolute value of x minus 2 opens as x minus 2. So limit when x goes to 2 plus of absolute value of x minus 2 over x minus 2 is equal to limit when x goes to 2 plus of x minus 2 over x minus 2. And since x goes to 2 but is never equal to 2, I can simplify, and x minus 2 over x minus 2 is 1. So I obtain limit of 1 when x goes to 2 plus 1, which is 1. The constant limit of a constant is the constant itself. So it is 1. But what is its limit from below, from left-hand side? Left limit of this function, of this ratio. Limit of absolute value of x minus 2 over x minus 2 when x goes to 2 minus Well, if x goes to 2 from the values less than 2, x minus 2 is negative. So the absolute value of x minus 2 opens as minus x minus 2. Minus 1 times x minus 2. So again, x goes to 2 from below, but it never reaches x. Is not never equals to 2. So we can simplify x minus 2 and x minus 2 and remain with 1, and there is minus in front. So we obtain limit of x when x goes to 2 minus of minus 1, which is equal to minus 1. Are they equal? No. The right limit is 1, the left limit is minus 1. You can see it from their slopes as well. Their slopes are different. One is negative, the other one is positive. So at this very point, in all the other points, there is no problem. This function is continuous and differentiable. But at the point 2, 1, when x is equal to 2, this function is continuous but not differentiable. Its derivative does not exist at that very point. In all the other points, it exists. You see? And a shorter way to see it is that when x is greater than 2, the absolute value opens as x minus 2. The function is equal to x minus 2 plus 1, which is x minus 2 plus 1, which is x minus 1. X when x is greater than 2, its derivative is 1. But when x is less than 2, then the absolute value of x minus 2 is minus times x minus 2 and plus 1. Which means when I distribute this minus 1 into the parentheses, minus x plus 2 plus 1, which is minus x plus 3, or 3 minus x, and whose derivative is minus 1. You see, the derivative of this part is 1 and this part is minus 1, as we see from the graph as well. Therefore, this function is continuous at the point 2, 1, but it has no derivative there. It's not differentiable. So, and here we have also the exercises of this part, both from the third issue of the book, the third printing and fourth printing of this book, and the solutions are in the solution book. So you just solve them, you try them, and whenever you don't understand anything, you can call me up or you can write me write me a message. Send me a message from my email or from WhatsApp or Telegram. So thank you very much for today. I just stopped the recording. And have a nice holiday all. Have a nice Bayram and holiday all.